It's all quiet.
Yeah, it's like half the time they don't even know what it is. Yeah, no, that's very nice.
Where's that taste? Oh, my husband is so strong.
When she was like, what? Like, what? She was like, I'm not
I couldn't find home.
Yeah, same.
Okay, so I thought we'd start with looking at some of the calculator functions that you're going to need. So it might be a good place for us to list them all down.
Are you going to be listing the purposes of the also?
Yeah.
Wait, is this going to be recorded?
Yeah. So 1 bar stats. Yeah.
Oh, did you pick up the record?
Oh shoot, I forgot to do that. Let me do it. Can I do it during break?
Yeah.
I know you said you don't have any more copies. Is there any way I can
Not right now.
Does anybody want to be members or borrow their
Okay, so first we have a 5-number summary. 1 bar stats gives you a 5-number summary.
Sorry.
Okay, the next calculator function. What else do we do? The plot, stat plot. Stat plots you can print or display. What's the first one? A histogram. A not dot plot, a scatter plot. What else do we? Oh, box plot. Okay. I don't think we use anything else in that's. So in chapter 2, we met the 2 very important functions, norm CDF. Okay, so that gives you the probability. The probability that Z is between A and B. What's that? Z cannot equal A or B? It's not really a one-for-one switch. No. Okay. Norm CDF, that also give me inverse norm. Inverse norm of, yeah. That gives z-score for gives the area for area A to the left, and that should be an A. That is more appropriate. Okay. Yeah.
For standard deviation, are we using the sigma or the S on the 1 bar stats?
Usually sigma. The next one, we're on chapter 3. We used the, what is that? Lin Reg. A plus bx, L1, comma, L2, comma, Y1. Okay. So that, L1, L2 computes the LSRL with the explanatory variables in L1, the response variables in L2, and also this stores the regression in Y1. What else did we use there? No, I think that's the only functions that we used there. The chapter 4, there wasn't any functions from the calculator. That was all division and multiplication. There's some formulas.
Was that the marginal conditional?
That was the marginal conditional distribution. Chapter 5, we did not have any calculator functions. No, we used rand int, right? And that gives a random integer
I have a question.
between A and B. Sarah?
If you're looking for a random integer, can't you just make one up on your
No.
own?
No.
Did you not do that?
No.
No.
The reasoning is that you may have a reason for picking the number that you're picking. And if you're going to write this in a scientific journal, you can't just say, so I picked number 3 because I felt like it.
Okay.
You know,
You have to do random.
yeah. There has to be some kind of a device that does the randomization for you.
Why does it look biased?
It does. It does. Okay, so that's, what was that? Chapter 5. Chapter 6 was about probability. So chapter 6 was a lot of just multiplication and division. I don't remember any specific calculator functions there. Yeah. Chapter 7, same thing, right? Now there were some calculator computations you needed to make, but that was all different. So that's kind of that. Anyone think of anyone else that we used calculator functions? The rest of this calculator stuff is like calculator like things that we did, but not a calculator function.
Can we also make a list of formulas we might need to know?
It's a long list. Chapter 1, then? Formulas? Mean? Do we need to know mean?
No.
No. Standard deviation? No, actually, you never have to do standard deviation on your own, right?
We always do z-score.
Yeah. Z-score we should know. But we're not quite there yet. Anything else from chapter 1? Oh, you know what? IQR?
Q3 minus Q1.
Yeah.
What do you have? You good? Closer? Yeah, that's good. You good?
Okay, so what was it? The IQR?
Wait, how do you find standard deviation? You don't need to. You don't need to?
Yeah.
How
Your calculator does that for you in one of our stats.
Oh, when you put in a list, right?
IQR, the high outliers is greater than 1.5 IQR plus Q3. A low outlier is less than Q1 minus 1.5 IQR. What other ONs do we have?
I don't know if this is possible or if there's a formula for it, but how do you tell the mean from a 5-number summary?
You can't.
There was one question though.
You can estimate it
How do you estimate?
based on if it's skewed right or skewed left.
Okay.
So if the 5-number summary looks skewed to the right, then the mean would be bigger than the median. Yeah.
Isn't it X bar? Wait, isn't it X bar?
Yeah. He's saying from a 5-number summary.
Wait, skewed
Which is
right?
like Q1, Q3.
Min Q1, median Q3,
Oh, I
maximum.
get it. But when you plug it in and you get bar stats, X bar is the mean.
Yeah.
Yes.
Yeah.
Got it.
So two different situations.
Yes.
In your situation, you're saying if you already have all the numbers, sure, compute the mean that way.
But
But in
use
Sammy's
something
situation, if all you have is the 5-number summary, you have to estimate it based on skewness.
If it's skewed left and the median is greater than the mean?
Yeah.
And then in a histogram, could you tell the mean? I don't know.
No. Same thing. You have to estimate it.
Is that the same thing as a box plot? You can estimate it?
Yeah.
Unless it's exactly symmetrical, right?
Yes. Yeah. And even then, I'd still call it an estimate.
Median
And
is
same with a normal distribution, the median is always the median.
Yeah. In a normal distribution, the median and the mean are exact.
Okay.
And a normal.
In a normal distribution. See, chapter 2, that's the z-scores, right? So a z-score is always equal to the measurement x minus the mean divided by a standard deviation. Okay. Area is equal to probability. And that's equal to the probability that z is less than a number, etc. There's like 3 or 4 of those that I don't want to go into. And then the z-score, of course, is the inverse norm. So if I have this situation, and that's the z-score, and that's the x, that would be the mean. Okay. The probability that x is less than a, no, sorry. The probability that the random variable is less than x is going to be equal to the probability that z, oops, sorry, z is less than z naught. Shoot, I'm sorry, I messed that up. X naught minus mean over the standard deviation, which is equal to the probability that z is less than some number z naught that you get out of that.
Mr. Ferreira?
Yeah.
So I'm pretty sure I understand the principle, but can you plug in like some number to show it in an example?
Sure. So if we know the mean is 12, standard deviation is, I don't know, let's say 3. And we want to know, let's make this 4. So the probability that x is less than 4, That's equal to the probability that z is less than 4 minus 12 over 3. And that means the probability that z is less than negative 8/3, so negative 2.33. Is it 6/6? And then you would compute that with your calculator. That's a very small number.
I have a quick question.
Mhm.
When do you know if the 1E99 is first or second again?
The way I think about it is at the very left here, you may want to think about this part right here is negative 1E99. And at the very far right here is 1E99.
Okay.
So if you want to know this area on the left, then you want to know between negative 1E99 and negative 2 point in the
Like
number.
those shaded at the end and see the numbers and what.
Yes.
Perfect. Great example. Thank you.
Okay. Of course, if you have this situation, and you know the area here is, let's just make it 0.6. That makes this area 0.4. And let's just say mu equals 12, and again, standard deviation equals 3. And if I want to know the 60th percentile, we're going to have to first get a z-score. So z is the inverse norm of 0.6. So we'll do inverse norm. Of 0.6. That's a z-score of 0.25. 0.25. And then we'll use our z distribution. So z equals x minus mean over standard deviation. So 0.25 is equal to the x, which is unknown, minus the mean of 12, which was given here, divided by 3, which is a standard deviation given here. And then 0.75, you would just solve that, let's see, 12.75. And then now you can just put all those numbers here, 0.25, 12.75. Okay. Okay, so that's a quick crash course on Chapter 2. Chapter 3, the formulas are a little bit more difficult. You don't actually have to know how to compute an LSRL by hand. You do need to know that R.
Can I ask something more about chapter 2?
Oh, okay.
It was on their review sheet. There were 2 questions on the review sheet that I just wanted clarification. One of them said the answer was that increasing the tails of the normal curve increase the standard deviation.
Yes.
I don't really understand that.
Well, standard deviation is a measurement of spread.
Okay.
And if you make the tails longer, you're making the spread larger.
Can you go up to like 5 standard deviations? Is that, so you're saying like if the tails spread out longer, you'll have 4, 5, 6 standard deviations?
Mm,
Okay.
yeah.
And then also, Okay, if you have, this was the one where you had two normal density curves, where their means were the same, but the standard deviation of one was 2 times that of the other. And then it gave you like 1, 2, 3, which is true, which is false. If, let's say you have population 1, and its standard deviation, or population 2, write this down.
Sure. You said you have normal distributions, right?
Yeah.
Okay, so we have a normal distribution. Let's do population 1. And let's just come up with a hypothetical mean. Say it's 10. Okay. And standard deviation is going to be, let's make it 2. That's 8. That's 12. That gives me 0, -1, and a +1. That tells you the mean and standard deviation right away. And you're saying there's another population. This is pop 1. You're saying there's another population that's also centered at 10?
Yeah.
But what about the standard deviations?
Standard deviation would be
4.
4. Yeah, it's twice the size.
So then this would be 6, and this would be 14. Okay?
And then it said, so like the first thing they gave you to see if it was true or false was that population 1 has twice as many observations within one standard deviation as population 2.
Okay, so that's false. We have no idea. Knowing the density curve doesn't tell us anything about how many people are in the population.
Okay.
It has nothing to do with it.
That answers that. And then the density curve for pop 1 is taller than that of pop 2.
So let's think about this, okay? The area between -1 and 1 has to be the same.
Right.
It's 0.68. Okay.
'Cause it's
That's the 67, 95, 90, 97 rule. That's the given rule for normal distributions, okay? So this area has to be the same. This area here is spread between 4 units. This area here is spread between 8 units.
so pop 1 has to be taller.
Pop 1 has to be taller
Okay.
because the area has to be the same.
So then let's wait. Which one has to be taller?
Population 1
Popular-
is the same area, but because there's smaller distance, it'd be taller in height.
This says that.
You know what? Read that exactly to me one more time.
Okay, the density curve for pop 1 is taller than that of pop 2.
No, read the question.
Oh.
Sorry.
Pop 1 and pop 2 are normal density curves with means and standard deviations, mu1, s1, and mu2, s2, respectively. Suppose that mu1 equals mu2, and standard deviation 1 equals 2 times standard deviation 2.
We have this backwards.
We do.
Yeah.
Yeah.
Population 1 has twice the standard deviation of population 2. So actually, this is pop 1 here, and this is pop 2 here. Population 1 has twice the standard deviation of population 2.
But no, but if you have standard deviation of if you have standard deviation of 2 for pop 1,
No one has to be 1 because it's like
but
Go backwards. If population 2 has the standard deviation of 2, population 1 has a standard deviation of twice 2.
oh yeah, okay. I got confused. Okay, we're good.
Yeah, so population 2 is taller than population 1.
Okay.
Okay?
Alright, good. Not bad.
It's fine.
What is that?
So let's just go back to chapter 3 with the means and all that. Sorry, with the linear regression. There's nothing that you have to calculate on your own necessarily. all of that, yeah, you use the linreg to do all your calculations. There are a few things you need to know. R is the correlation coefficient. Okay. It gives,
gives us correlation.
yes, gives a rough description of, maybe rough is wrong, but it gives a description of how closely the scatter is, how do I describe that? Yeah. It gives a description of how close the scatter is clustered. Okay.
It's like even if it's negative, it could still be highly correlated.
Yeah. R is always between -1 and 1. And 1. Okay. R and R that is close to 1 or -1 is how do I say this, is almost linear. R has no units. R and slope have the same sign. So if you have a negative slope, then R is also negative. If you have a positive slope, then R is also positive. The important, or the one that can throw you off, is R does not tell you if the points, or if the scatter is actually aligned. You can get,
You can stay here one more day. I want to work.
yeah, you can compute R even if the points are clearly curved. He's in my first period. He wants to know if he can leave some stuff here. I don't know what the stuff is.
Sketch.
Is that sketch?
Yeah.
Yeah? Yeah, Jordan?
I recall from one of the chapters a discussion about resilience to something.
Yeah.
Is that?
That means that if there's an outlier, will it make your measurement change dramatically?
Yes, it will.
Yes, and linear regression is not resilient.
It doesn't make a difference if there's an outlier?
Meaning
Or it does, it's not it.
that an outlier can drastically affect the regression.
So, what is resilience?
There's no number that goes along with resilience. It's just a descriptor. Is it resilient? Is it not resilient?
So, is there anything that we've learned that is resilient to
Median.
the median?
The median is resilient.
Um,
The mean is not resilient.
Isn't it resistant?
The median is resistant.
Like it won't be effective.
Yeah,
But the mean,
the median is resilient.
but the mean is, get it, I get it.
Wait, are resilient and resistant opposites?
Resilient and
Resistant.
no. Don't-
It's the same.
I don't know what resistant is.
The notes say resistant.
Resilient should be resilient.
Oh, it's resilient.
Sam?
I'm confused by R does not say if scatter is actually aligned. I thought it told.
It tells you how closely they are kind of in a line, but it doesn't tell you if they actually are in a line.
So it could be like a spiral.
Well, it could be a curve.
But,
Like, if I had points that are in a parabola, I can compute a linear regression for it. Right? That doesn't mean that the linear regression is good. Okay.
but I thought that R could tell you if it's actually line because if it's near 1, it's going to be a line.
It means that, yeah, it just means that the scatter's close together. Okay. Maybe we
Is
should.
there an equation for R, or do we just...
You just do your calculator. Resilience.
After, will you give us an example of that?
Resilience means not
Not affected by an outlier.
affected by outliers. So resilient. Resilient measure is the median. Not resilient. The mean. LSRL. This is part of the reason why if you have a skewed observation, or if you have a skew observation, you want to use the IQR as a descriptor. So it's more resilient.
Can we go through once more how to find all this stuff?
Which one?
Like LSRL,
I kind of want, can we go over, finish all this and putting us all down there? Okay,